Hello and welcome to another video on orbital mechanics. We're still going through the book Orbital Mechanics for Engineering Students by Howard D. Curtis, and we're following on from what I did in the last video. I'm going to go over some theory on the time derivatives of moving vectors, and we're moving on to a concept of vectors in arbitrary vectors in a moving frame contained in an inertial frame. So what I have in front of me here is a inertial frame Z, Y, X with axes K, J, and I, capital K, J, and I. And within that frame there is a moving frame, which is lowercase x, y, z and lowercase I, j, k. Attached to that moving frame there is a vector b that is moving arbitrarily, and the moving frame is rotating and moving arbitrarily as well. The inertial frame does not move. And so to conceptualize that into some formulas, I'm going to start on a clean page. And we have the vector b, which can be defined as bx I lowercase plus b y j lowercase plus b z k lowercase. Now this is all from the book, but I think I can make it a bit simpler and maybe explain it a bit clearer, I hope. So starting with this vector, we can take the derivative of that vector. That's the position vector. So we're going to get the velocity vector, right? So that would be d b by dt equals, now the I, j, and the k are the axes of the moving frame. So these actually have a time component. So when we take the derivative of these, they're not constant. So we have to use the product rule for each piece. So that ends up being d b x dt I plus d by dt j plus d b z dt k plus, on the other side of the product rule, bx di dt plus by bj dt plus bz dk dt. So that's each piece of product rule there. You're doing product rule 3 times, one for each component. And from our previous video, we found that for a constant magnitude vector, it can be defined as dA by dt equals the angular acceleration times the vector, the cross product of vector. So we're going to replace these di by dt, dj by dt, and dk by dt because they're all constant magnitude, but they are rotating. That's fine. We're going to replace them with this formula here. So we end up with so d b dt equals d b x dt I plus d b y dt j plus d b z dt k plus the symbol for angular velocity in this case is, blimey, the Greek hat. Can't even remember what it's called. Cross multiply by bx I plus by j plus bz k. I could have just wrote b, but anyway. And then we also know that this is actually the relative vector, so we can go ahead and substitute that in. So that's just equal to db dt relative. Now this relative is essentially just meaning that we're using the it's the derivative of the b vector within the relative space. So you can see it's derivative here of the b times our moving frame. So that's what that means. Plus and then we take the second derivative of that. So d2b dt squared equals d dt db dt relative plus the derivative of the angular acceleration cross b plus the angular acceleration cross db dt. That was the product rule again. And that equals this component here can become this. So relative plus angular velocity cross multiplied with vector b. So we can multiply those out, but we won't do that just yet. Now we can also say that d dt db dt relative is equal to d2b d2t relative plus angular velocity cross multiplied with db dt relative. Now that equation comes from essentially this equation. If we imagine that is b, we can replace b here and here, and we get this. So we'll substitute this back into here, which equals d2b dt2 relative plus angular acceleration cross multiply db dt relative. Let's put that in brackets. And plus okay, it's a bit messy, but that's d2b over dt squared relative plus angular velocity cross multiplied derivative of b relative plus angular acceleration cross multiplied with b plus angular velocity cross multiplied with derivative of b relative plus angular velocity cross multiplied with b. A bit of a mouthful. Let's collect up those bits together. So d2 b dt2 relative plus angular acceleration plus angular velocity cross multiplied angular velocity cross multiplied b plus 2 angular velocity cross multiplied db dt relative. The problem in the book is problem 1.12, and it's asking for us to find the absolute velocity and absolute acceleration of a point P. So here is another display I made earlier, and we have the inertial frame and the moving frame and the point P. And point P is defined by this relative vector, and this point O is defined by this RO, and then there is this R which goes from the origin here up to P. So R equals R origin plus R relative, and we can take the differential of that, and it gives us the velocity equals the velocity at origin plus the differential of the R relative. And we can define R relative as being the velocity relative plus the angular velocity cross multiplied with the R relative. And this comes from this equation here, which we effectively just did. I show you. It is here. So we're just putting in our B vector, a relative vector in there. And this here ends up being the same as velocity relative. So then when you put that back into here, V equals V naught plus V relative plus angular velocity cross multiplied with the R relative. Now this sort of makes intuitive sense, because if the point was actually at the origin, if P was at the origin here, there would be no component added on from this. The velocity would just simply be the velocity of the origin plus the relative velocity, which again would be 0. So as you move away from the origin, the speed from your angular rotation is increasing. So, and this is the formula for angular velocity when you want velocity out of it. V equals WR, this being W, omega, sorry, angular velocity. So that works. Now the tricky thing about these is you have to remember to make sure your final values are in the inertial frame reference. So this will actually be defined in terms of lowercase I, J, K in the moving frame. So you need to multiply out the components of this vector with the lowercase I, j, k, which is these, in order to get the final answer. And then this is the equation that we just saw earlier here, but with the terms replaced in meaningful ways for movement. So acceleration, relative position, relative acceleration, relative velocity. And again, these all need to be converted into the inertial frame reference. The inertial frame reference when you add them up and do your cross multiplies. So I've done a MATLAB script to work out the answer to 1.12. It's just a matter of plugging in these values. And I guess going back to the theory, it's not terribly complicated. It's just a bit messy. So starting off with the vector, you take the derivative, you use a product rule, and then you replace the axis derivatives with this, and then we then end up with this equation here. We say that this is this, so this is the derivative of the position relative. So that's why the I is there. And these are lowercase x, y, and z, right? So you need to be careful with these. The lowercase x, y, and z is the x, y, and z in the moving frame. If this was a capital X, Y, and Z, it would be the position in the inertial frame, and then it would be multiplied by whatever these are. So you need to make sure everything is consistent. And then replacing, taking the second derivative, it's the product rule, and then we're effectively finding things that we can replace with simpler terms or terms that we have at our disposal, and using this equation we get this definition from here. So that's straightforward. And then we're just simplifying and collecting down to this. And like I say, that is acceleration, and that is relative acceleration and relative position. And just make sure your axes and your initial conditions are coming from the right source. You should get the right answer. Thank you very much. Bye bye. If you have any questions, leave them in the comments. Thanks. Bye.